So we know that in the first law, we relate the change in the internal energy with the heat and the work of a system. This is the principle of the first part. In the second part, we discussed the kinetic theory of gases. So we apply the ideal gas, we apply the relationship between temperature, pressure, kinetic energy, and speeds of molecules. And also, we apply the relationship between mean free path, between the diameter of molecules, or also the number of molecules per unit volume. Okay, and then we study the molar specific heats, right? The molar specific heats at several special cases. So I hope that you remember the basic thing. For example, the expression of the first law, the four special cases of the first law, or the way we use the kinetic theory of gases, especially the ideal gas law. Also, some gas constants. I think you will refine it during the midterm exam and also the final exam, what I said. So today, what we will study again today is the last part of the thermodynamics, the entropy and the second law of thermodynamics. Entropy. Do you see my slides?
Yes.
Good. Wait for me. I stop sharing, then I make it full screen. Do you see it?
Yes.
Good. So I think you might heard about the entropy already and the second law of thermodynamics. If you have time, you can already go online, or you heard somewhere of the word entropy. Then what is entropy? Of course, in Vietnamese, we cannot translate it. We do not even have the similar word, so we also call it entropy in Vietnamese. That's why I say that there's no help of translating things from mathematics, from physics, from chemistry into Vietnamese. We learn it directly using English. Okay. Now, entropy has a very big meaning. So far until now, I haven't mentioned about the irreversible processes. But actually, in reality, we have mostly irreversible processes and not reversible processes. What we studied previously was our gas sample confined in a cylinder, okay? And we consider that there's only the change between the internal energy, the heat, and the work. So I mean, the energy is conserved. So somehow, we have reversible processes. But in reality, we have always, for example, the loss of work to the environment. Then in this case, we cannot restore 100% the work or the heat to the change in internal energy, right? We cannot restore 100% of them. Then in this way, we have irreversible processes. And if you pay attention, the irreversible processes always have a direction, right? Have a direction. For example, I give you some example here. An egg is dropped onto a floor. So this is one direction. The egg will be broken. There's no way that we can restore one egg that is already broken, right? So you see that this process goes from one way only. So we have the egg in our hand, we drop it, it will be broken. There's no other direction that the egg from the floor will go into your hand and then will gather together to have an intact egg, right? A pizza is baked. So we have an uncooked pizza. Then once we cook, we know that there's only one way. There's no way that a cooked pizza will become again an uncooked pizza, right? So we know that the irreversible has a direction. Then we understand also that these processes can go only in one way, but why? For example, you have a car and it is driven into a lamppost. Then you know that the day after you will have to put it in the garage to fix it. There's no way this accident will be resolved and your car will be fixed by itself. So if we talk a little bit more about the reversible processes and the irreversible processes, we can say that the reversible processes are the processes in which the system is in equilibrium with its environment. And for irreversible processes, we do not have this equilibrium. Okay, we do not have it. But the question is, why? Why these processes are reversible, right? Why? There's one way, only one way for us to explain it is to accept the notion of entropy. Entropy. So the idea of entropy provides a mathematical way to encode the intuitive notion of which processes are impossible. So we know that which one is possible and each one is impossible, right? We know it by institution. Về trực giác là chúng ta biết là cái gì có thể xảy ra, cái gì không thể xảy ra, đúng không ạ? Nhưng làm sao để giải thích nó? But how to explain it? But we have the idea of entropy. And this entropy will provide us an explanation in a mathematical way to explain it. Then we know why we cannot preserve irreversible processes. Good. If you look in most of the book, a lot of references, it will say that the entropy is a matter of the molecular disorder or randomness of a system. I will talk about the word disorder or the randomness of a system later. But here you understand that this is a matter of the disorder or randomness of a system. And this term was coined firstly by Rudolf Clausius. Okay, Rudolf Clausius in 1865. He was the first one mentioned about this word. And this word was originated from the Greek, and so it's the in, okay? Top is a turning. So we have entropy is actually in a turning point. In a turning point. This is the meaning of entropy. This concept was developed in response initially to the observation that a certain amount of functional energy released from the combustion reaction is always lost. Okay, we have the loss during the combustion due to the disposition or also the friction. Yeah, and so this loss is not transformed into the useful work. That's why in the next step you will see the link between the heat lost from the system and the change in the entropy. Because originally this concept was developed to explain the observation that in a real system we always have loss of energy. Then there are two ways that we can define the entropy of a system. There are two ways we can define. We can use a microscopic perspective, or we can use a macroscopic perspective. Okay? Then after we study the two ways to define the entropy of the system, we should be able to explain this figure. Why when we put a hot block and a cold block, we have mostly this situation. We have the situation that the two blocks have the same temperatures and not one is very hot and one is very cold. Why do we always have an equilibrium, thermal equilibrium, right? We will try to explain it using the two ways. I will go into the first way, the microscopic perspective. So in the microscopic perspectives, we will count the ways in which the atoms or molecules that make up the system can be arranged. Okay, in a microscopic perspective, we try to explain the entropy as the state in which the atoms or the molecules that we use to make up the system can be arranged. In the macroscopic perspectives, we try to explain the entropy in terms of the system's temperature and energy, okay, that the system gains or loses. So we have two ways to define the entropy, our entropy, the microscopic perspective, and macroscopic perspective. I will go to the harder one, and we will see it together. So for the first approach, the microscopic perspective, what we have. I don't know if the figure, if you can see well the figure here, I have 2 rooms. I take the picture of the 2 rooms. One room, the first one here, do you see it? Is more ordered, okay? And the number 2 here, the room here, is more disordered. If you just look at it, right? Các bạn thấy là cái phòng thứ nhất này, tôi đưa cái hình ảnh thì các bạn có cái cảm giác đúng không ạ, là nó gọn, nó ordered hơn, nó gọn gàng hơn, nó trật tự hơn là cái thằng thứ hai đúng không ạ? Ngọc Ánh có thấy thế không ạ? Hay là em thấy ngược lại, phòng em giống cái thứ nhất hơn hay cái thứ hai hơn?
Nhìn cái hình nhỏ quá.
I make it bigger, okay? Wait for me, I make it bigger. Do you see it? Or is still small? Anyway, you see here, you can have perception that the number 1 is more ordered than the other one. Or it depends on you, I don't know. Maybe Ngọc Ánh think that, oh, this one is more ordered. This one is ordered. I'm not sure. But for me, this one is much more ordered than this one. But we do not know that this one has less entropy than this one. So the disorder of a system is very different than what we think of the word disorder usually. Cái mà cái gọi là disorder của một cái system thì nó không giống với cái sự là trật tự hay không trật tự mà chúng ta thấy bằng mắt thường. Okay, so someone that is messy, this one is very messy. Okay, we use the word messy, should be different than entropy. So the entropy do not say about the messy, something that is messy. For example, here we have the moon and here we have the sun. Which one is more disorder than the other? So if you look at here, you can say the sun, right? I don't know, maybe you have a thinking is that the sun is more disordered than the moon. But actually we do not sure. What we need to do is to really look at their entropy. So here, the disorder of the entropy, we should define it as the number of states that a system can take on. I will explain, okay? The number of states that a system can take on. Okay, what is it? I give you a very simple example. I'm sorry, may I take a break for 2 minutes? I will give someone some details. Hello? Okay, I'm sorry, I'm back. Now we continue. We consider two systems, okay? Two system, very easy one. One system have 4 atoms, only 4 atoms. And the other will have 8 atoms. What? Here, if we see 4 atoms, we'll have fewer possible states. So the way these 4 atoms can be arranged for each possible arrangement, we call it a state. For a system of only 4 atoms, it will for sure have fewer possible states than a system having 8 atoms. Do you agree with me? For example, here we have 4 colors. Yellow, I don't know other colors. Here, this is one state. If we change the position of the yellow one, to here to the blue one, we have another state. Or this one, if we change it, we can have another state. But even after all the arrangements, you count the number of the arrangements, you will see that this system will have much fewer possible states than this one, because this one have more atoms. So here we say that this system also have more entropy. More entropy. Okay, so we can understand entropy is really the number of states that a system can take on. And Boltzmann, was the one defined the entropy as a measure of the number of possible microscopic states of a system in thermodynamic equilibrium. A measure of the number of possible microstates of a system. This is entropy. In a microscopic perspective. You understand here? If you understand here, I think it's quite easy to understand. I also try to be slowly to explain the entropy. If you understand here, we consider another problem and we try to find a way to calculate also the microstate and also the entropy of that system. Now we have another system. We consider a box having 6 identical molecules of a gas. So these molecules are identical, okay? So we cannot distinguish them. And this is these 6 molecules are contained in a box well insulated. Good. So at any instant, a given molecule will be in either the left or the right half, having the same volume of the box. Here or here. At any instant, we consider the number of molecules having in the right half and in the left half of the box. So the molecules will have the same probability of being in either half. Do you agree with me? Because we cannot distinguish the right half or the left half. There's no difference. We also cannot distinguish these molecules because they are all identical. So we have the same probability for the 6 molecules of being in either half. You agree with me until here, right? I continue. Now, what we study is the possible configurations of the 6 molecules. The possible configurations of the 6 molecules. What do we have? Here we name it the first configuration, number 1, number 2, number 3, and so on. We will see the first configuration. The configuration, where is it? Here. Number 1 is the configuration that the 6 molecules are found in either the left half or in the right half, right, of the box. Here, for example, the number 1, we have 6 molecules found in the left half. All the 6 are found in the left half. Number 7, all the 6 molecules are found in the right half. Similarly, we have the configuration number 5 here. We have 2 on the left, 4 on the right, and so on. Right? So we collect the configuration for the other half. Then we continue. Okay, is it okay here? We can continue. So each arrangement, like I said, we call it a microstate. Okay, we call it a microstate. Here, if we use a little bit of mathematics, this is what we have. If we use a little bit of mathematics, we will have the total number of ways in which we can select all 6 molecules if the products of these independent way. In other words, it is actually the factorial 6. This is a little bit of statistics. I don't know if you already studied statistics, basics of statistics. Hello. I'm sorry, I have a phone call. So the total number of ways in which we can select all 6 molecules is the factorial of 6. So here we have 720 ways that the 6 molecule can rearrange in our system. But because what we see is that the 6 molecules are identical, so we cannot distinguish them. So there are several ways that this one will become this one or this one. We cannot, because we cannot distinguish them. Then we have to eliminate, okay? We have to eliminate the microstates who are identical. Here, this way we calculate when the 6 are all different, then we may have 720 independent ways. But now, because the 6, they are all identical, then we have to eliminate the microstates who are identical. Văn phòng gọi tôi. Now, how to get the number of different arrangements? So we eliminate the arrangements who are identical, right? Then we will have a formula in mathematics. We call it the multiplicity. So the multiplicity of configuration is actually the number of microstates that correspond to a given configuration. We will have this one. Okay, this is a little bit of mathematics. So if we calculate, for example, the multiplicity for the configuration number 1, we use the formula, we can have only 1. So there's only 1 arrangement for the configuration number 1. For the number 4, for example, there are 20 different arrangements for the configuration number 4. Good. So, and so on. Is it okay? So for the situation that half of the box will have 3 molecules, and half if the other box will also have 3 molecules. We see that this configuration has the biggest number of microstates. Has the biggest number of microstates. Yes, we have n equal n1 plus n2. I think already written here. Okay. So the total number of microstates is 64 for this case, okay, for our case. We see here the configuration 4 is the most probable configuration. And the probability for this configuration to take place is that 20 over 64, right? So the probability, because we have 64 microstates, here it takes 20. So we can have a configuration for the system. So the system is in the configuration for 31.3% of the time. Good. And the
but why I can come up with the formula like 6 6 factorial divided by 6 factorial times 0 factorial.
This one. This is
calculation process.
This is mathematics. Okay. You have to do a little bit of statistics to get the number of different arrangements. So this is the formula to calculate the different arrangements. I cannot explain you why, but this is the way you calculate it. You have to do a little bit of statistics, the basic of statistics. Is it okay? For now, if you not study, you accept it. This is the way we calculate. Now I continue the configuration 4. This corresponds to the situation that the molecules are evenly divided between the two halves of the box. Okay. And this is also the configuration that we see the most statistically. If we see again the configuration 1 and 7, the probability for it to happen is only 1.6%. It's only 1.6%. And these are the most probable configurations for our system of only 6 molecules, of only 6, right? Yeah, so we see that the probability to find all 6 molecules in 1/2 of the box and the other half is empty is very small, even for a system of only 6 molecules. Then for large values, for example, 1 mole. 1 mole is already very small, okay? 1 mole of the sample is already very small. But in 1 mole, we have 6 times 10 to the power 23 molecules. So much bigger than our system. Very big. If we apply for a very large values of n, what we see is that nearly all the microstates will belong to the configuration in which the molecules are divided equally between the two halves. Okay, here our system of only 6 molecules, we already see that the probability to find half is already the highest. Now, if, for example, we have 1 mole, then we will see that nearly all the microstates will belong to the configuration 4 here, configuration that we can find the molecules divided equally between the two halves. And for the configuration 1 and 7 here, yeah, it will mostly 0, very close to 0. So the probability will mostly like nothing. Good. Ở đây là nếu chúng ta xem một cái hệ chỉ có 6 nguyên tử, phân tử, mà cái khả năng là cái 6 cái phân tử này được phân bố đồng đều ở cả hai nửa nó đã là cao nhất rồi. Thế nếu như mà bây giờ ta có số mol chẳng hạn, 1 mol chẳng hạn, 6,23 nhân 10 23 nữa thì chúng ta sẽ thấy là nếu chúng ta áp dụng đúng như thế này, chúng ta sẽ thấy là cái configuration mà mỗi bên ấy, ở trong cái hộp của chúng ta, mỗi bên có một nửa số phân tử nó là vô cùng cao, và cái trường hợp mà tất cả các phân tử nó dồn về một bên ấy thì vô cùng gần với cả số 0. Nó gần như là không thể xảy ra. Đấy là ta mới chỉ tính cho 1 mol thôi nhé. Và trong thực tế thì không biết là bao nhiêu mol. Good. So, and to go further, Boltzmann also derived a relationship between the entropy and the configuration of a gas and the multiplicity. And this is the Boltzmann's entropy equation. So we have S, so the entropy of a configuration here is actually the product of K, here K is the Boltzmann constant, times the ln of multiplicity. Here, this is what we call the Boltzmann's entropy equation. And to calculate the entropy, okay, of each configuration, we apply this formula. Here, this is what we already calculated for our system of 6 molecules. So what we see here is that the entropy of the configuration 4, so half-half, is still the biggest. Okay, it's still the biggest. So we see the entropy associated with the configuration 4 is also the biggest. So this is the way we define our entropy in terms of microscopic approach. Good. For this subject and in the framework of the first year, we do not pay much attention, pay much time on this approach, but I present it to you in a very precise way for you to understand the notion of entropy, the way to calculate entropy in terms of a microscopic approach. What we need to pay attention on the framework, in the framework of this year, is the second way to define, to define the entropy of a system, the macroscopic perspective. So we define the entropy in terms of the system's temperature and energy that the system gains or loses. So this is the main focus in the framework of the first year. Before we go to the second part of the lesson today, please, we can do this small exercise. Now we suppose that there are 100 molecules in our previous box, and these 100 molecules, they are also indistinguishable. Then please try to calculate the number of microstates associated with the configuration half-half. So we can find half of the molecules in half of the box and half of our molecules in half of the other box. And we compare with the configuration that 100, so all of our molecules are found in one half, okay? And in the other half, we have nothing. We try to calculate it. Ok, bạn Hoàng Việt Thanh nhé. Các bạn đi tiêm mũi 3 rồi à? Chả nhẽ bây giờ cứ đi tiêm trường kỳ. So, who can do it?
Number A is 100 factorial divided by 50 factorial square.
Here.
Actually, no, the calculator.
Yeah, you need to have a calculator to be able
No,
to.
I mean the calculator solve it either. Like we only like a normal calculator can only get 100 digits and not 157.
I cannot hear you.
So yeah, my calculator can't get that many
Let's
digits.
do it. It's also not a problem. You can go to Google and you can find the calculator online. It will help you to calculate it. Okay?
Okay,
Because this is it's true that this is a very big number, and but I also exclude this part in the final exam. What I want you to see here is that you understand that for our very big systems, our system consisting of a big number of molecules, then the possibility for the system to reach an equilibrium. Yeah, the possibility for our system, every system, to reach an equilibrium is the highest. Okay, so you just have to understand it. It doesn't matter that you can calculate or not. Good. In this way, you can explain why. You can explain this one. Like I said, I'm sorry. Where is it? You can explain this one, for example. You can explain why when we put a hot block and a cold block, so all of the time we have this situation. So the blocks after some time will have the same temperature because this is the configuration that has the highest probability to be happen. Okay, so this is the meaning and also the idea that I want you to understand. Đúng không ạ? Sau khi các bạn đã xem tất cả ấy rồi thì các bạn sẽ giải thích được vì sao mà khi chúng ta cho một cái thằng rất nóng tác dụng với một thằng rất lạnh thì cái trường hợp này nó luôn xảy ra này, là trường hợp sau một thời gian là hai thằng nó ấy bằng nhau, chứ nó không phải một thằng vẫn rất nóng, một thằng vẫn rất lạnh. Đúng không? Bởi vì đây là cái trường hợp mà nó có cái khả năng xảy ra là vô cùng cao, cao nhất theo statistics. Và cái trường hợp mà một thằng vẫn nóng nguyên, một thằng lạnh nguyên thì nó bằng không. Nó rất gần với không nếu như tính theo toán. Và trong thực tế thì là cái trường hợp này nó cũng bao giờ là cái trường hợp xảy ra nhiều nhất, vì nó là cái xác suất khả năng của nó xảy ra, nó gần như chiếm là tuyệt đối với một cái hệ vô cùng lớn. Good. Giống như bây giờ chúng ta sẽ xem cái sự thay đổi giữa một cái hệ mà có 6 phân tử thôi và một cái hệ có 100 phân tử thì nó đã là như thế nào. Mà 100 phân tử nó vẫn là một cái hệ vô cùng bé. Yeah, just like now we will see the difference between one system having only 6 molecules and one system having 100 molecules. And we know that even for 100 molecules, this is also a system, a very small systems in reality, right? very small. And for this even very small system, what do we have? The configuration of 50-50. So I mean the equilibrium is this one, 10 power 29, okay? 10 power 29 microstates. And the configuration of half-half, yeah, I'm sorry, configuration that 100 microstates, 100 molecules are found in one half of the box. It's only one. It's only one. So you see the difference between this one and this one. The difference between the configuration 50-50 and the configuration 100-0 is the factor of about 10 power 29. So, okay, it's very, very big. So according to the probability, this one mostly never happen, and this one will mostly always happen. Good. So if you get the idea here, you can explain why we always have the equilibrium and why the process can only go in one way and not the other. Okay, it will go to the way that have the biggest microstates, yeah, and cannot go to the way that there's mostly no microstates. So I think we can take a break here for 10 minutes, and then we will go to the second way to define our entropy.
So I want to ask another question. So a room from the room that you showed me from the physics point of view is more disordered or messy because there are many ways to make that room messy. Is that right? And there are not so many ways to make it tidy.
Sánh đúng không?
Yeah.
Chưa thấy mấy các bạn nào nghe thấy Khánh nói không?
Yeah. So,
what he was saying that
yeah.
What he was saying that in the physics point of
you
okay, what he was saying that is that in the physics point of view, there are the mess room, the room analogy that you used earlier has more entropy because there are many ways to make it messy.
So we cannot give a conclusion here. So you talk about this. Here we cannot come up with a conclusion. If we want to come up with a conclusion, we also need to know, for example, how many atoms are there in this room, or how many atoms are there in this room. Okay.
It's just an analogy, something to make you understand it easier, right?
I don't understand. Yes.
Oh, what I'm saying is that it's just an analogy, something to make you understand it easier, not like a complete description of what entropy is.
Exactly. I just want you to distinguish what something that is messy doesn't mean that is more disordered. Okay. When you see something that is messy,
it's more probable.
Physics kind of view.
So you mean the higher entropy, the more probable it is going to happen?
Yeah. Is it okay? For example, if you consider each items in this room,
atom,
then you should measure, you should count how many ways can arrange these items in this room. And
that
here,
is fine.
so we should also count how many ways we can arrange this item in this room. If we consider that each item in this room and in this room is identical, then in this way we can compare. Is it clearer? But if we look at rooms like this, we think that this one is more ordered. Okay, vì sao tôi lại để ở trong ngoặc kép more ordered and this one is more disordered. But we cannot tell anything in terms of physics point of view, in terms of entropy. Đúng không ạ?
Okay.
Is it clear? Good. Nếu như giả sử như là các bạn ở đây này, mỗi cái item ở trong đây này các bạn coi là một cái phân tử đi, thằng này cũng thế đi, ta cứ coi là tất cả hai thằng nó giống nhau đi. Thì giả sử muốn nói là thằng này ordered hơn hay thằng này disordered hơn, là thằng này có entropy nhiều hơn thằng này, thì các bạn phải xem có bao nhiêu cách sắp xếp các cái item của phòng này, các bạn đếm ra. Và cái thằng này cũng thế, các bạn xem là có bao nhiêu cách sắp xếp các cái item của phòng này, thì lúc ấy các bạn mới có thể so sánh được là thằng nào nhiều entropy hơn thằng nào more ordered hơn thằng nào. Ok.
Với cả một cái cách sắp xếp là một cái microstate đúng không thầy?
Đúng rồi, mỗi cái arrangement là một cái microstate đấy. So, is it okay? We take a break of 10 minutes. Nguyễn Nhật Anh hỏi câu gì đây? Hỏi ngoài lề khi tác dụng cùng một lực vào hai vật bằng kim loại có thể tích khác nhau, thì khi đạt mốc nhiệt độ một giá trị, không hiểu câu hỏi, thì vật nào đạt đến nhiệt độ đó sớm hơn? Không kể đến sự như này. Khi tác dụng cùng một lực, tác dụng cùng một lực vào hai vật bằng kim loại có thể tích khác nhau, thì khi đạt đến một mốc nhiệt độ. Tôi không hiểu câu hỏi lắm.
Thì ý câu hỏi của em là thì có hai cái vật, có hai, trong trường cụ thể ở đây là có hai cái thanh sắt, thì có một thanh lớn hơn thanh còn lại. Thì khi dùng búa gõ vào hai thanh cùng một lực ấy, thì nếu mà mình đặt một cái mốc nhiệt độ là lớn hơn cái nhiệt độ ban đầu của nó ấy, thì khi mà đã tác dụng rồi thì vật nào sẽ đạt đến cái mốc nhiệt độ đó sớm hơn?
Cái này thì tôi cũng chịu, bởi vì cái chuyện mà nó còn tùy vào cái bề mặt tiếp xúc. Nếu như mà thực nghiệm mà nói thì em đo nhiệt độ em chỉ đo được ở một cái vị trí chính xác của nó thôi. Nếu như em tác dụng cùng một cái lực ma sát hay cùng một cái gì đấy và em đo cái nhiệt độ ở đúng cái vị trí mà em ma sát thì nó sẽ là như nhau. Nó liên quan tới cái chuyện đấy mà. Đó, nhưng mà em đo ở một cái chỗ khác nhưng trên cùng cái vật liệu thì tôi cũng không thể nói được, bởi vì lúc ấy nó liên quan tới cái việc truyền nhiệt, đúng không?
Thì nếu mà gõ vào đúng cái vị trí đấy thì cái nhiệt nó tỏa ra thì nó sẽ, thì những cái cả cái vật bằng sắt đấy nó cũng sẽ trung hòa nhiệt độ đúng không? Tức là nó sẽ một bên nóng một bên lạnh ấy, xong rồi là hai bên cân bằng nhiệt ấy.
Bao giờ nó cũng có cái cân bằng nhiệt.
Thì cái để
Nhưng cái này thì tôi cũng chịu không ấy được. Chắc phải đo. Tôi thì tôi nghĩ nó cũng như nhau thôi, có thể là sau, bởi vì tôi chưa rõ là em hỏi. Bây giờ giả sử em có hai thanh sắt, em cùng tác dụng một lực ma sát đúng không? Giờ em muốn xem cái thằng nào nó nóng lên nhanh hơn thằng nào chứ gì, hay như thế nào? Em
Vâng,
đạt.
thằng nào nó nhanh hơn đến một cái nhiệt độ nhất định.
Thực ra thì nếu như mà em xét tới cái khối lượng thì em có cái Q bằng mc delta t rồi đấy. Một cái thằng nào khối lượng to hơn thì nó sẽ cần nhiều nhiệt hơn. Nhưng
Vâng.
đấy em xét cả tổng thể cả cái thanh sắt của em. Bởi vì nó liên quan tới khối lượng nhé. Khối lượng có nghĩa là nó được express bằng cái chuyện là một thằng này nó nhiều cái phân tử hơn thằng kia. Thì em muốn làm nóng nhiều phân tử hơn thì em phải cần nhiều nhiệt lượng hơn. Hiểu ý tớ không? Còn nếu trong thực tế nếu là một thanh sắt bản to và cái cặp nhiệt của em mình gọi là cái cặp nhiệt đó là em chỉ đo được cái nhiệt độ ở đúng cái vị trí mà cái cặp nhiệt nó tiếp xúc thôi thì lúc đó thì tôi không rõ.
Thế thì thì cái vật nào nó nóng nhanh hơn thì vẫn chưa xác định được đúng không? Hay là nó phải cần nhiều hơn một cái điều kiện đấy thì mới được?
Đây nhá, em bây giờ em cứ nghĩ nhất đơn giản em xác định là Q bằng mc delta t đúng không? Bây giờ em muốn cho delta t nó bằng 1 độ đúng chưa?
Vâng.
Thì mình có một thằng là Q1 bằng mc bằng m1c1 đúng không? Q2 bằng m2c2 đúng không? Cho là cùng một vật liệu đi thì là Q bằng m1c, Q1 bằng m1c và Q2 bằng m2c đúng chưa? Cùng tăng lên một
Vâng.
nhiệt độ mà. Thế thì ừ, cái thằng mà có m to hơn ý, thì nó cần Q to hơn đúng không? Thế thì em
Vâng.
muốn nó lên một cái nhiệt độ với một cái khối lượng nhiều hơn thì em cần nhiệt độ nhiều hơn
Vâng.
đúng chưa?
Còn vâng, còn về là cái việc tác dụng,
Đó
còn về cái khả
nhưng cái thứ hai mà mình bảo bởi vì là tôi làm về nhiệt mà tôi nghiên cứu rất sâu về nhiệt thì tôi mới bảo em thêm là trong thực tế giả sử em có một cái thanh sắt mà tiết diện của nó là độ 2 cm và cái đầu tiết diện của cái đo nhiệt độ của em chỉ có 0,01 cm vuông thôi, trên một diện tích 2 cm vuông thì cái chuyện là em chạm cái đầu nhiệt độ ở đâu thì nó chỉ đo được cái giờ nhiệt độ ở cái chỗ đấy thôi.
vâng. Tức là trong cái khả năng cái đầu của cái nhiệt nhiệt kế rồi đúng không?
Ừ, đúng rồi. Thế nhưng mà
À, và
nếu
em
nói là cả một
vâng.
cái liệu hay cả một cái vật của em mà nó thằng nào nó nóng lên nhanh hơn thì em dùng cái công thức rất đơn giản QMC delta T, nó là cái năng lượng có thể mất đi hoặc là nhận vào của vật để cho tăng một giờ giá trị thì, nhiệt độ của nó lên.
Vâng,
Rồi
em hỏi thêm một chút nữa là về là cái việc tác dụng nhiệt, tức là có một tác dụng một lực lên một cái vật kim loại ấy, thì với mỗi kim loại khác nhau thì nó cũng có khả năng chuyển nhiệt khác nhau đúng không?
tới tất nhiên
Vâng, vâng, anh cảm
cái
ơn.
ừ, kim loại nào nó chả có cái hệ số truyền nhiệt khác nhau, nó là cái ừ, nó liên quan tới cái MC của em đấy, specific heat đấy.
Vâng,
Ừ, nhé, liên quan tới cái specific heat của em đó. Ok chưa? Tôi đi uống nước một tí rồi tôi quay lại nhé. So please, we resume. Please turn on your camera and also we come back. We continue. Now we consider the second way to define the entropy of our system. Bạn Nguyễn Thiên Ân đang trên ô tô à?
Vâng ạ,
Học hành kiểu thánh đấy.
em thấy cái này tập trung hơn thầy ạ. Em cầm điện thoại nên là không bị sao nhãng bởi những tin nhắn.
Okay. Now, now we continue. Please come back. In terms of microscopic perspective, then we define entropy as the matter of the system's thermal energy per unit temperature that is unavailable for doing useful work. Okay, because the work is obtained from ordered molecular motion. So the amount of entropy is also a matter of the molecular disorder of the system. Okay, that's why here we have the explanation, for the amount of energy lost due to friction and so on, due to the heat transfer. And this is also the way that we use the entropy to explain in our system of the gas. Because what we consider is the way a system can store energy, can transform into heat and work. And we know that originally when we studied the engine, we try to find a way to explain the energy lost due to friction, due to other things. So I mean the energy that we cannot convert it into work. Okay, and in this way we define the entropy. So the entropy in this way is the thermal energy per unit temperature that is unavailable for doing useful work. Okay, and if we see the entropy in this way, we see the link between entropy and the efficiency of our system. Okay, that's why sometimes we say that we can use entropy to explain the efficiency of our motorcycle, of our car, and so on. And when we see the entropy in this way, we will talk about the change in entropy. The change in entropy. Gia Bách đang xem cái gì, như đang xem phim, xem phim gì mà mặt tớn hết cả lên, mồm thì không ngậm mà được. Hỏi tới thì không biết gì. Good. The change in entropy can be calculated using this. So the thermal energy per unit temperature is Q over T. Okay, this is entropy of one state. Now the change in entropy is actually the final entropy minus the initial entropy, right, of a system. And this is the integral, yeah, of dq over t. So the differential heat, so very small change of heat per unit temperature. Good. You see the similar way that we define, for example, the volume. I'm sorry, the work. The work is also the integral from Vi to Vf of P dV. So we sum every small part of the change of pressure and volume. We sum it up. We sum every small change of work. Then we have a final work. Here we sum every change of entropy from state I to state F. Then we have the final change in entropy of the system. Okay, this is the way we define the change in entropy. The integral is the sum, right? And here, this is the small change of heat per unit temperature. Đúng không ạ? Đây cách chúng ta định nghĩa sự biến thiên entropy này. dq là những cái sự thay đổi rất nhỏ của nhiệt lượng này trên một cái đơn vị gì ạ? Nhiệt độ này. Đó. Và tổng của tất cả các cái thằng này đó, từ điểm đầu tới điểm cuối này, đây là tổng này, thì nó sẽ là biến thiên entropy của cả hệ này. Đó. This is the way we define it. And what we see here, that the change in entropy depends only on not only on the energy transferred as heat, but also the temperature at which the transfer takes place. So it depends on both the heat and the temperature at which the transfer takes place. Good. And it will have a unit of joule per Kelvin. This one is joule and this one is Kelvin. So the unit is joule per Kelvin. Nguyễn Đức Dũng đâu nhỉ? Camera sao đen xì đấy.
Không bật đèn ạ.
Ok, hỏng hết mắt bây giờ. Now we continue. Is it okay until here? When the temperature change is very small relative to the temperature before and after the process, then we can rewrite the change in entropy, which is this one. So which is the heat divided by the average temperature. This is only when the temperature change is small, okay, related to the temperature before and after the process. Good. Or a constant. If we have a constant pressure, then this one becomes T. For an isothermal process, for example, the change in entropy is actually the ratio between heat and temperature. Since when we have no change in temperature, we can write it like this one. And here, what we know using, how to say, empirically, we see that entropy is a state property, or we also call it a state function. Actually, a state property is also a state function, okay? So it depends only on the states and not at all on the way the system went from one state to the other. It depends only on the states, okay? The entropy depends only on the state and not on the way the system went from one state to another. Good. Here, empirically, we find it because sometimes there's no way for us to prove it mathematically, especially for irreversible processes. But we find it. There's one way for us to find the entropy change for an irreversible process. Is that we will replace the irreversible process with any reversible process that connects the same initial and final states. Since we accept that the entropy is a state function, so it depends only on the initial and the final states. Then to find the entropy change, we can replace an irreversible process with a reversible process that have the same initial and final state. Good. So here, there's one way we can prove it, but only for reversible process. We can prove that entropy is a state function, but we can prove it only for reversible process. Okay. How to do so? Now, we can start from the first law, and we consider it in the differential form. We have this one, right? The differential internal energy equal differential heat minus differential work. So this is the first law in the differential form. Good. Then if we rewrite the heat, we should be able to have this one. The work here, differential work equal P dV, right? If we consider that the pressure is a constant, the internal energy, differential internal energy is NCV delta T. This one we know. Good. If we apply the ideal gas law here, then we change actually the expression of pressure. So the pressure become nRT, right, over V. And if we divide both sides to the temperature T, we will have this expression. We will have this expression. And what we see here, the differential heat over temperature here is the entropy, the change in entropy, right? Yeah, we take the integral. So I mean the sum. We take the integral from the initial state to the final state. Here we have the expression of entropy And here we have another expression. You see, here we have another expression. So now the entropy can be expressed as a function of volume and temperature only. Yeah. Then the change in entropy can be written like this. Good. So this is what we see. We see that here the change in entropy between the initial and final state, but depend only depend only on the states, on the final state and initial state. It does not depend on how the gas changes between the two states. So do you see? Here we just need the initial state. So we need the initial volume, the initial temperature. Here we need the final volume, the final temperature. Then we should be able to calculate the change in entropy. Good. That's why we say that it depends only on the initial and final states, just like the change in internal energy. Is it okay? This is for reversible process. We can have a way to prove that entropy is a state function. Yeah. And also this is the reason why for irreversible process, the way we find the change in entropy is that we replace this irreversible process with another reversible process having the same initial and final state. Yeah. Khi mà các bạn đã chấp nhận được là entropy nó là một cái state function, thì có nghĩa là cái độ biến thiên entropy nó chỉ phụ thuộc vào cái initial and final state, đúng không ạ? Thì các bạn nhớ là state, for example, of a gas, is defined by their properties, by its properties. For example, the one state of a gas can be defined by the pressure, by a combination of pressure, temperature, and volume. So we have a state of a gas. Khi mà các bạn đã chấp nhận là cái entropy nó là một cái state function, thế thì các bạn có thể có một cái cách tính độ biến thiên entropy cho các cái irreversible process, tức là các cái chu trình không thuận nghịch, bằng cách là các bạn thay nó bằng một cái chu trình thuận nghịch mà có cùng điểm đầu và điểm cuối. Đó, bởi vì chúng ta có cách để chúng ta tính được cái entropy cho các cái quá trình thuận nghịch, nhưng chúng ta không có một cái cách để chúng ta tính entropy trực tiếp cho các cái chu trình không thuận nghịch. Bởi vì với các cái chu trình không thuận nghịch thì các bạn thấy cái integral này, cái dấu tích phân này nó sẽ không áp dụng được. Ở đây tôi có một cái bài tập các bạn sẽ hiểu rõ hơn cái mà tôi vừa nói. Here I have an example so you will understand better what I just explained. I have two blocks. Okay. I have two blocks of copper. One block that has higher temperature than the other block. So we have the warm block with a temperature TL. So from the left, and we have a colder block having a temperature TR. At the beginning, there's an insulation wall that separates these two blocks. Good. When we remove that wall, then an irreversible process will take place. An irreversible process, right, will take place. Because we know that this will transfer energy to each other in the form of heat. And this warm will become colder, and this cool will become warmer. And at the end, we will have a thermal equilibrium. This one you know already. We try to explain it in the previous part. Now, how to calculate the net entropy change of the two block system during this irreversible process. Yeah, I give you 5 minutes. Okay. Now, here, this is the solution for this exercise. So we know that this is an irreversible process, right? an irreversible process. But we can find a way to find, we can find a way to solve it. Please wait for me a little bit. Oh, can you see it?
Yes.
Okay. So what we want is to calculate the entropy of this irreversible process, right? And we cannot calculate directly, but we know that we can find a reversible process that takes the system from the initial state, okay, to the final state. And then we can calculate the net entropy change of that reversible process. And this is also the entropy change of the irreversible process. Is it okay? So for this way, we can choose a reversible process. Yeah. We can choose a reversible process in which the thermal reservoir, in which the temperature can be changed slowly. Can be changed slowly. Is it okay? Now we start to establish the change in entropy for a reversible process. You understand? Here, because the formula here, okay, is work only for reversible process. Then we will find a reversible process that has the same initial and final state. Then we apply the formula. Is it okay? So what we have here, the heat will equal mc delta T, right? The heat will equal mc delta T. And the integral will become from Ti to Tf. From Ti to Tf. And here we have Ti is actually the temperature of the copper, right? But the colder one. Then we can rewrite the expression of the change in entropy equal mc, the integral of dt over T. And this becomes mc ln of Tf over Ti. Is it okay? Then what do we have? What we have is that we calculate the change in entropy of the colder one, so of the cold cooper. You will have this value. You apply the same thing, okay? You repeat the same thing here for the hotter. I think the hotter is here. Anyway, one of them. So you repeat the same formula for the hotter one. Good. Then you will have the change in entropy for the hotter one. And our system actually is the combination of the two blocks together. So we see if we calculate the change of entropy for the system of two blocks, then we have an entropy of 2.4 joule per Kelvin. So this one is bigger than 0, right? During the second law, you will see that we will have a change in entropy that is always equal or bigger than 0. And for an irreversible process, we always have a change in entropy bigger than 0. So this is the entropy calculated for our reversible process. Okay, for our reversible process, we can only apply this one. Yeah, if this is a reversible process, that's why you have to explain it at the beginning. And since we find the change in internal energy for our reversible process, this is also our change in entropy for our irreversible process. Is it clear here? Cái công thức, các công thức này, bởi vì các bạn phải có cái sự liên kết điểm đầu điểm cuối đó, thì các bạn mới có thể dùng được công thức này, và công thức này nó chỉ áp dụng được cho những cái gọi là chu trình thuận nghịch thôi. Cho nên là khi mà các bạn tính thì các bạn phải lập luận được là vì entropy nó là một cái state function, nó không phụ thuộc vào cái đường đi, đúng không ạ? Thế thì cái irreversible process thì có thể cái change in entropy, cái độ biến thiên của entropy của một cái chu trình không thuận nghịch thì có thể được tính toán bằng cách là tính cái độ biến thiên entropy của một cái chu trình thuận nghịch mà có cái điểm đầu và điểm cuối giống hệt. Thế khi các bạn lập luận được như vậy thì các bạn mới bắt đầu các bạn tính toán các cái công thức ở đây. Good. Về mặt tính toán thì nó đơn giản, nhưng về mặt bản chất thì các bạn phải hiểu như vậy và các bạn phải lập luận như vậy. Khi mà các bạn biết đây, các bạn được cho là một cái chu trình thuận nghịch thì tính entropy như thế nào, các bạn không thể tính trực tiếp được, mà các bạn phải dựa vào entropy của một cái chu trình thuận nghịch để các bạn tính toán cho một cái entropy của chu trình không thuận nghịch. Is it okay? What else?
Okay, sir.
Yeah. Now, please, we have another small exercise. This is our system. So here we see another irreversible process, right? Another irreversible process, which is a free expansion. Here we have our gas and here we have the vacuum. So we know that when we open the stopcock, we have a free expansion, and a free expansion here is an irreversible process, so we cannot reserve it. how do we calculate the entropy change for this irreversible process? Good. How do we calculate it?
Also, is this free expansion adiabatic?
A free expansion is also an adiabatic process. Yes, but you cannot apply the formulas developed for a normal adiabatic process. You remember what I explained you already, because actually there's no connection at all between the final state and the initial state of of a free expansion. So in a free expansion, what we know is that the change in internal energy equals 0, the heat equals 0, the work also equals 0, and the temperature, okay, the initial temperature equal the final temperature. So this is one hint that you can use. Free expansion, what we know. Everything equals 0, you cannot calculate, right? The heat also equals 0, you cannot calculate. The temperature, initial temperature equal the final temperature. How do we calculate? The change in internal energy.
There's a change in the initial volume and the final volume. There's a change in the initial and final volume of the system.
No.
What?
The volume?
Yes.
Yes. The volume of the gas double. Yes. Of course.
So we can take the reversible is like NR.
What process, what reversible process we can use here?
The change in volume.
More precise.
NR.
So actually we have the initial state, the initial temperature and the final temperature is the same for our process, right? So the easiest way, is to choose an isothermal process, right? Having the same change in volume. So we will have the same initial state, right? Ti and Vi is the same, and Tf, Vf is the same for our free expansion. But since in our free expansion, Ti equal Tf, so it comes that we will choose what? A reversible isothermal process. Good. Reversible isothermal process. Then you calculate the heat I'm sorry. Các bạn có thấy cái slide của tôi ở ấy lớn không? Ở màn hình lớn không?
Không ạ.
Nó đang ở màn hình
Chưa
nhỏ
thấy
ạ.
thầy ạ.
Không ạ.
Vẫn đang
Không
màn
thấy
hình
à?
nhỏ.
Không.
Lớn chưa?
Rồi ạ.
Rồi ạ.
Rồi. Yeah.
Very nice. So here now when we could already define our reversible isothermal expansion, then in this way we can start calculating the change in entropy. So the heat, like you do as usual, like you saw it. So the heat equal this one for an isothermal process and RT ln VF over VI. So this is the heat for an isothermal expansion, right? And the change in entropy is simply the heat over the temperature, because here we also have no change in temperature. Good. You should be able to calculate it. So the change in entropy for our reversible isothermal expansion is this one. Good. And finally, we have the change in entropy for our irreversible process. I mean, our free expansion process here is still the same. Is it okay? So you see here, you cannot calculate the change in entropy in a direct way, because free expansion, the heat equals 0, and you cannot calculate. Good. But if you do like this, then you can calculate the change in internal energy. The change in entropy for our free expansion process. Good. So I think we stop here a little bit. In the last part, I will discuss with you about the second law of thermodynamics. So second law is very simple, but then the entropy in the real world, then we will see some applications of the second law. So we have the engines and the refrigerators. We see each other in 10 minutes.